Welcome to F453 by Jam. Today we are covering Chapter 3, Computer Architectures. In the contents are von Neumann architecture, registers, the fetch, decode, execute cycle, and other machine architectures. John von Neumann contributed to many areas of mathematics and computing. Before von Neumann architecture, programs were fixed and would need rewiring to change the program. Von Neumann introduced the idea of the stored program, where programs would be stored in the memory as a set of instructions. This architecture uses the fetch, decode, execute cycle. It has a single processing unit, which completes an instruction in its entirety before moving on to the next one. The program and data were stored together in the same format. To this day, it is the most commonly used architecture. Registers. Von Neumann architecture uses a variety of registers. You should know what registers are and how different registers such as the program counter and memory address register are used. A register is located in the processor. Each register is used for a particular purpose, as we'll see shortly. Registers are used for temporary storage and can be accessed quickly. Here are the types of register you'll need to know. Program counter stores the number used to find the next instruction in memory. Memory address register holds the memory address of the next instruction, used to fetch the instruction. Memory data register, sometimes called the memory buffer register, temporarily holds the program instruction from the address in the memory address register. Current instruction register holds the instruction to be executed. There are two parts to an instruction, the opcode and the operand. The accumulator temporarily stores results from the ALU. The ALU can only do one calculation at a time. In larger calculations, it must remember answers to parts it has previously calculated. The program status word keeps track of the current CPU state. The interrupt control register generates interrupts. Fetch, decode, execute cycle. Von Neumann architecture uses registers to perform this cycle. Firstly, the number stored in the program counter is copied to the memory address register. The number is then incremented by 1. The memory address register stores a list of addresses. The address with the index of a program counter's number is used to load an instruction, which is copied to the memory data register. The instruction in the memory data register is then copied to the current instruction register. The current instruction register then decodes the instruction. The instruction in the memory data register is then copied to the current instruction register. The current instruction register then decodes the instruction. If the instruction is a jump instruction, the operand is used to load a new value into the program counter. It then resets the cycle. If not a jump instruction, the instruction is executed. When that is done, the cycle is reset. Remember that this cycle is repeated continuously. Other machine architectures. Millions of pixels are drawn on your computer screen in a fraction of a second. A single ALU would take ages to calculate the colors for them. Let's look into some other architectures. A coprocessor is an additional processor used for a specific task. It improves the overall speed of the computer. For example, a math processor is good at handling floating point numbers, which the main general-purpose processor would struggle with because of its length and complexity. The fetch, decode, execute cycle has 3 main phases, hence the name. Pipelining takes advantage of this by using processors that handle different parts of the code. SISD stands for Single Instruction, Single Data. In the traditional method below, we have completed 3 jobs within the given time period. We had to wait for the entire instruction to finish before moving on to the next one. Now let's have a look at pipelining. We have split our all-purpose processor into 3 specialized ones. Let's look at this step by step. Firstly, job 1 is fetched. Once that is done, job 1 is decoded. But now the fetch processor is free to fetch job 2. Once job 1 has been decoded, it is executed and job 2 can be decoded, and so on. You can see that the throughput speed has been increased. Just look at the gradient of the graph. 6 jobs have been completed in the same time period, as opposed to 3. Pipelining is faster while full, like this. Array processors are another kind of computer architecture. This one is single instruction, multiple data. The processor contains multiple ALUs. The same instruction is used to operate on several data items at the same time. Array processors are used in graphics cards. You would apply an instruction to every pixel in real time. Parallel processing is the multiple instruction, multiple data architecture. There are multiple independent processors that can share data and work on the same program. It's useful for handling large amounts of data because many things are done at the same time. The speed is not limited to the bus transfer rate. However, data that relies on the results of a previous operation cannot be made parallel. This means that programs have to be written specifically for this type. It's also more expensive than the other architectures. Parallel processing is dominantly used in supercomputers and weather forecasting. RISC and CISC are two contrasting architectures. RISC has a small, simple instruction set but complex programming. CISC is the other way around. The additional example shows that more instructions are required in RISC to do the same in CISC. Note that CISC instructions have to be decoded to sub-instructions. RISC has one cycle per instruction, but more instructions would be in the program. This also means it uses more RAM. CISC has larger, richer instruction sets, so the hardware is more expensive. Both have their uses. RISC is used in mobile phones, for example, and CISC in personal computers. That's all my slides. Thank you for watching. Strike that like button and subscribe for more F453 related content.